So, hello everybody, and welcome to a new episode of the Solar Journey. My guest today is Jürgen Sutterlüti. Welcome to the show, Jürgen.
Hello, Torsten. Great to be here.
Yeah, thanks for joining. So, let me briefly introduce Jürgen. So, Jürgen works for an Austrian company called Gantner, and he's the vice president in the energy segment. And he's responsible in that role for cloud services and marketing. So his business units provide services for monitoring and controlling energy assets. And so Jürgen helps to optimize the operation of solar power plants and battery parks. And the methods used for these services are edge computing devices and cloud-based processing. Before joining Gantner Instruments in 2014, he worked for Oerlikon Solar and Tokyo Electron Solar, where he was responsible for optimizing PV power plants. So Jürgen has been in the solar industry for quite some time, and power plants were always on his mind. His background, Jürgen studied power electronics and systems engineering in Austria and Switzerland, and he holds an MBA in entrepreneurship from the University of Liechtenstein and University of St. Gallen in Switzerland. So Jürgen, when and why did you get started in solar?
Well, great welcome from my side also to everybody and all the listeners. Well, when I did start in solar, it was, I think, roughly 2003 when I did my master's on the university, where it started with renewable energy and all the IPCC reports, where they are starting to get a bigger topic. And there were also a few niche applications for PV and a few companies around who thought there is some potential in solar. And then we did learn that. I did also do a lot of courses for renewable energy systems and also see the global energy change. You know, the BP reports were a big thing at that time. You have to understand where all the oil is coming. And I tried to understand how this system works. And it's a hot topic up to today. Maybe it's switching now to gas, but still it's oil and coal and gas dominated system. But it was clear that that system has to change because everybody knows that peak oil is over and already passed. So people are looking to keep their power, but still move to some new applications. And then I had the chance to work in the university to set up a renewable energy institute where we did a lot of PV. And at that time in the Rheintal Valley, there were also a lot of activities for starting coating activities for solar industry, which was Oerlikon Solar, obviously. Coming from the big Oerlikon group has a perfect coating experience. A lot of people know it from Balters and so on. And PCVD was needed. And then we could start and work a lot of out for new PV feasibilities and so on. Also inverter manufacturers, transformer-less manufacturers were there coming to the market. So we did test and analyze and model a lot. And that was quite intensive and also fun to see the different journeys where the different players are going. And that built a lot of competence, and it was a very good self-financed institute. So we had more than 50% industry financing. So the demand was there. And this brought a lot of foundations there. And then you start to do papers, then you start to meet people in the industry. And that was one of the first phases entering solar.
Yeah, excellent. So from the university you switched to Oerlikon. What was your initial job at Oerlikon?
Yeah, I mean the timing was perfect because there was a demand for doing something when a PV module was produced out of that end-to-end turnkey production line. Oerlikon at the beginning has not a concept that they do turnkey. They wanted to sell just equipment. That's the same trend as the people are doing now. Also, again, you had and so on. So the PSCVDs and Kai machines were more or less there a key thing. And then they decided to build up a turnkey thing, and then you need somebody who understands what should the PV module look like, what is coming out in the outdoor conditions, and how do you link outdoor measurements to flasher measurements, and then building up their team and working also very close with the researchers in Neuchâtel. So I had access to very bright minds where I could work with them, test their new cells, modules, testing the latest stuff from the pilot line. I think you know that feeling and you know that journey as well. And so we try to understand what's coming out in the real world. And there are a lot of discussions why it's not as it is in the flasher. And that was always a motivation for me to understand that, even against resistance. Because, standard test conditions are for indoor, and outdoor it's something else. And on top of everything, it was very clear that it's kilowatt hours per square meter. And this is what makes the win. And this win, we tried to really ride the wave with thin film, because crystalline was very expensive and so on. It's expensive again today, so that's also a driver for new technologies. But you also had to mount that modules, so we had working a lot of system designs. What is the PV module looking like? So a lot of trends what First Solar used, for example, we also initiated and did their things, a lot of power plants, and this was more or less the early journey. This was then getting bigger and bigger, so we had to convince customer in the home market. So we started test power plants across the globe, from Alice Springs to the US. These cans and power plants next to each other, so we have local data for India and so on. It was also fun to control and set up everything, and there it's the first step of collecting all the data, because you had to have optimized reporting, otherwise you spend too much time on Excel files and so on. And you also have to select the right database, which was then a good starting journey and learning effect for my work at Gantner.
Sounds pretty much like it.
But coming back then to the power plants, you know, it's always then that you want to compare. You always have to compete as a new technology versus established ones, and if you don't show the benefit up front, you are not there. So it was very intense and also very strategic, that you have to show track record, and you cannot accelerate track record in the field, so you have to install early the stuff, and we did that at several locations worldwide.
Excellent. So lots of engineering that drove your initial career, but always with the focus on the economics, the profit from solar power plants. And you did an MBA on top of your engineering degree, or actually two, if I read correctly.
It's a combined one. It's just one.
It's just one and combined. What was the driving force? Was it worth it? And would you do it again, or should you have gone business first? Should you have skipped engineering when you look back now? Or
no, I think the people in the market are very helpful when they can understand both worlds. And that's also my interest. For me, it was also very clear that I'm not a full 100% researcher, but I want to bring something to the market and see and identify new trends and use that technology to create value. This is what drives me. And when you see new ideas, when you see a new energy generation source, I wanted to test that. That's why I also went to wind industry and developing converters and understand what happens when a DC-AC converter blows up and all that stuff. So I was really on site repairing that stuff, the cooling liquids, and accidentally hitting the shutdowns and so on. So that's all experience which you have to have, because when you do some strategic things and more business related things, you cannot run the world by Excel or business plans. Somebody has to do it at the end. And when you can judge that, what it really means, I think you can work with the team in a different way. And I think that's the way how I want to work with people, and also how we have to have project development nowadays.
Excellent. So what was the key thing you learned during your MBA, which you didn't learn during your engineering course?
Well, I think it's very important that you can communicate your idea, what you want, and that you have to spend a lot of time to simplify it down for the right audience, and that you have to be quick adapting to the audience, because that changes over time and over the day. And if you don't understand what you're doing, people will discover that very quickly. So don't talk about things, or be open when you don't know things.
Yeah.
And be honest. So that's a little bit my main takeaway. The MBA was about entrepreneurship because I want to understand and learn that. As a technician, you saw that a lot of startup was a hot topic, and I wanted to understand what are the rules and how you work with that VCs and all that stuff. And that was a very good background, that you have an understanding about how it works. Also, digital marketing is something what we touched there. So it was a lot of topics which I understand at that time very well. And it was one of the first entrepreneurship studies in Europe with excellent profs. So we benefited there a lot, and that's helping me up to today, that you have a little bit of understanding how the business world works.
Excellent, excellent. Thanks for that. I'm sure that many listeners consider moving on from one direction, engineering or business, to the other side, and yeah, this could be helpful input for some of the listeners. Hey, a few words on Gantner. So how many people work at Gantner? What are the other segments? Roughly the revenue, global footprint. Could you share some some information on Gantner?
Yes. So Gantner Instruments is an Austrian-based company headquartered in Vorarlberg, so close of Lake of Constance and in the Montafon. So a
Beautiful
nice place
area.
to work.
Yeah,
exactly. Blue sky today, snow on the mountains, so perfect work place. But it's a very distributed and flat company, and it was founded in 1982 with a lot of different applications, from access systems, from RFID detection system and data acquisition. And the investors at that time, they had said, too many different segments does not make sense. We have to focus. And then the data acquisition system was one which was one up for sale. And then our current CEO, Mr. Werner Ganal, and a colleague, they bought that out, and then he was running Gantner Instruments, which is then doing data acquisition and control. And that was and one application in that area is mobility, automotive, combustion engine nowadays, EV testing, battery testing. The other one is aero and space, so rocket launch pads and so on. So also very dynamic growth now in the Space Coast. So we have clients in that Boeing, Airbus area, which brings also the mindset of a company into the product, because even when you're in a small valley, you have to delivering for the world. The second thing is that we have then also condition monitoring and civil engineering applications for railway and so on. German railway, for example, are big customers from us. And then we have energy, and within energy, we're doing wind, solar, battery, and also hydro power plant monitoring. And PV is the latest add-on on the growth journey, because PV started quite small and is now 30% of the turnover already. Overall, we make we make 25 million plus, and we have more than 100 people across the world. We have offices, own offices from San Diego to Singapore to in China, Paris, Stockholm, Germany, two in Zwönitz and in Nuremberg, and headquarter in Austria. So it's like a very flat organization. R&D is done in the headquarter, and sales and business processes and talking to the people is very decentralized. That helps us that we get very early the trends from Asia, what they at the end will be implemented in or demanded in the US, and Europe is in the middle. We have more or less 24/7 of support with all their teams, which makes us accessible. And the focus is that and that was not just because it's now hip, it's at the beginning that you listen to the customers and deliver rapid prototypes and feasibilities with them. So we go the journey with them. It's partnership, not just a vendor. And that brought us to a lot of cool projects, and that's a lot more or less the spirit how you grow in the new markets. Yeah. For example, we are also doing in the energy segment fusion energy, which is always delivered in the next 30 years something. So, but this is shifted all the time. But you know that fusion reactor in Greifswald, North Germany, all the data acquisition comes from us, and even the Notaus, the emergency stop, is controlled with Gantner. This is like a flagship project, and you don't get in there if the quality is not good. Period. And due to that, we are also working in ITER and all that stuff. And the same examples are applicable for a lot of different applications. So we have all the automotive players which are doing their testing with Gantner. Really globally. So you have to have people in Michigan, in Detroit, you have to have people in Munich, in Stuttgart, which are there talking to the customer, working with the customer. Okay, and the great success story is our PV business unit. It's separated in a separate company, because we all know that solar is a high volume, low margin business, and there is a roller coaster. And it started quite small and is growing exponentially. So at the beginning, the story was that we have data loggers as a product. And then Schüco was in the market and said, we will do a house. We're selling all the components, and we also need a data logger. So we were trying to sell data loggers to Schüco. That was the current CEO from Gantner Instruments Environment Solution, Jürgen, who is doing there a great job. And then Schüco stopped immediately. And then, what we do? The next thing was, well, string monitoring is a topic. Why we don't measure strings? We can monitor and data log everything. So we did start with string equipment. And then this was a huge market. We did ship hundreds of channels, thousands of channels to India and all across the world. And then you start to grow. You do combiner boxes, turnkey, ship that in containers to the solar boom in Australia and so on. So that team has a great know-how about logistics and doing big projects. And at the beginning, it was, a megawatt and 10 megawatt. And nowadays, smallest projects are not below 50 megawatt. It's huge. What they are working on is currently, is 400 megawatt, the biggest one in Germany. And this is done turnkey with Gantner monitoring, hardware and control. And you need a good team who understands the value chain. Yeah. And string monitoring is not the most important thing for the industry all the time. You've seen it's going down in Europe and globally, but you see small signs again in the US at the moment, which is funny because they always rejected string monitoring. And of course, with decentral inverters, you don't need that. You have all the data. So the next step was in the evolution that you do data logging and control of the power plants. So we have already all that stuff. And now power plant control is one of the key services. And we differentiate there clearly that we have an open platform and the customer can adapt the control mode. So it's not a black box, it's a platform. And we can support that remotely. from everywhere in the world. Connectivity is key there. And with that, we control with one data logger hundreds of megawatts and collect the data at the same time. And this is, there are more than 10 gigawatts out there with control of Gantner at any moment of time. So if this is not working, we would have a business problem. So reliable control is key.
Yeah. So your system, is it it includes hardware, right? So it's not only software, it includes
it's hardware and software.
It's hardware and software. So you monitor the performance of single small units in the solar park, but also now the full complete solar parks. So what kind of data do you collect, and what does your customer do with it, and what's the value you create with this monitoring?
Yeah, this answer has to be different per stakeholder group.
Okay.
Because
who are your stakeholders?
Exactly. I will try to group that. So you have different type of phases also in the last 10 years. You have the EPCs in Germany, which build and want to sell after 2 years. So they go for the fast delivery. It has to work. They want to get their PPA signed or feed-in tariff, and then after 2 years they want to sell it. They don't care about the data quality. You know, if I may formulate that in that clearness. But the second one who will buy it, he then has to integrate the data again into his platform. So you have already two players. The one is the EPC, and the second one is the one who is doing a portfolio management.
May I jump in? So the EPC, does he already include your monitoring, or he just doesn't care? It's just extra cost.
No, he is including it. You have two types of companies. A lot of them say, "Oh, I don't need it," but that was the early days. Nowadays, monitoring is defined there, and it's below 0.5, 0.7% of the total system cost. So it's neglectable. But when you want to ramp it up, when you want to sell electricity to the grid, you need that data. So it's nowadays no longer possible that EPCs can say, I don't do monitoring, just do the metering. I have to be clear also, when we talk about that, we talk about utility scale. Gantner is not doing the residential and so on.
Yeah.
We do a lot of power plants in the air, you know, commercial rooftops for the big mobility brands and all. But then you aggregate that together. Okay, but they always have their platform, our cloud-based solution, software as a service. They see instantaneously what is there. So they see if inverter is broken, they have the ticket system, they have a document system and all that stuff, and track record. Good. And the first 2 years is everything is good installed, then it's fine. Then you sell it, and then other people want to log in, and then they want to migrate the data. So we are having a separate world, which is more or less the platform management, that all the power plants are in there. This is the biggest customer scope. And they, of course, want then to have reporting, portfolio management, how is the performance ratio of different power plants, and alarming and notifications. So you see if the inverter is broken and so on. Okay. And the third one is the one who really wants to produce kilowatt hours and sell that on the energy trading platforms. They want to optimize the system. And when you want to optimize, you have to understand what is my current performance versus my expected performance. And their modeling and loss analysis comes into the game.
Yeah. Excellent. And so you have an initial CapEx, and with the software you have a recurring revenue business model, or how does it work?
Yeah, we have the hardware is based on the requirements from the RFP, and all that stuff is combiner boxes and all that stuff. So you have that they purchase it, then they own it, and the cloud-based service is a monthly fee that starts on 20 euros per megawatt. That's roughly the price. And for bigger projects, then you optimize that, and then you have additional services for controlling and so on.
Yeah, excellent. And You mentioned that you're using edge computing. That's a term which you hear now a lot often, but what does it actually mean? Edge computing.
That's correct. It's a buzzword, and since Gantner is doing data loggers since 1982, maybe we are the oldest edge computing company in the world, but that's all what I want to say about edge computing. No, it's about data reduction, because when you have, let's take in Egypt, we have in Benban, there they plotted this multiple plots of 50 megawatt power plants there, and then you have one controller absorbing everything. Maybe you do two controllers because you have a road in the middle of the PV power plant, so, and you want to control it, or you have different owners, so you have two or few, let's call it data loggers in the field. Now you have to acquire all that data at the same time, because if it is shifted by a few minutes, it's worthless for analysis later on. But we do that on a 1 second rate everywhere. So that's and we are ready also for higher sampling rates already, because if you see that in industries, PV is really still relying on 5-minute or 50-minute average values, but customers now use 1 minute, but there's an next trend will be 1 second and or faster for a specific time. And for that, you need data reduction, because you can, with our technology, stream data up to the cloud on 10 hertz, kilohertz basis for grid quality thing. But you have to reduce that. First of all, if there's no internet connection, you have to buffer it locally. Not everywhere in the world you have a stable internet connection, or at least wired. So you have to, the team is dealing with all that satellite concepts and so on. And you also want to trigger activities even when there is no cloud like control. So edge computing is more or less an intelligent device which can work standalone even when you are not connected to your cloud service. And customers can put functions on that platform, so they can apply rules, they can adapt, feed in strategies. That's also helpful when we talk about batteries later on. And you can also record data on a trigger based. So for example, when you have tracker movements, that you just measure the force and the motor current when the tracker is moving, and you don't store data when the tracker is doing nothing. And that can be applied for all different things. And out of that, you can also do some local logic. And that has to be fast and not just on a Gantner is able to do real-time control. So in the high-end performance devices, you can acquire the data with 10 or 100 kilohertz, which is needed for power quality and battery explosion testing. That's too fast what you need for PV, but for PV, we use that know-how and just cost optimize it for the solar use case.
Yeah. Another buzzword to edge computing is artificial intelligence. So you have lots of data. Are you providing services in that sector as well? So you have, can you show correlations between wind and I don't know.
Yes.
Tracker accuracy, anything like that?
Yes. And it all starts when you understand one PV device and then you scale it up to a utility scale device. So we have also a product line which is doing IV scan testing outdoor. That's more or less the DNA of the PV module. When you know how that behaves versus temperature gradients, you can already start to model that. And there we still work with mechanistic, which means physical, meaningful modeling, and not just machine learning. Because when you predict something, you want to hear what happens or what is not okay, but the answer you need also is the why. And machine learning is so far not able to tell you why you have a power drop. The latest trend on machine learning is that you have explainable AI now in the field, which is a hot search topic, that people try to develop AI which is explainable, what AI is doing. So we test that, we do that also intensively, because it helps you if you have no data to sanitize and to group. But on the PV world, you still can do a lot of mechanistic modeling. And there we are in a range of plus minus 2.5% normalized root mean square error for the prediction of the power output for any component in the power plant. So that's a lot of calculation, but it's you just need irradiance, module temperature, and if it's windy, wind sensor, and with that modeling we can really predict the power at any given time. And the same also for voltage and current, and that also helps us a lot for the fault detection.
So Jürgen, thanks a lot for the explanation. Just to make it more transparent, so you measure IV, so the current and the voltage from in this case the solar power plant. What else do you measure? It's wind speed. Can you give us an idea of the number of data points?
Yeah. So that's in the thousands. So you want to, when you have string monitoring inside, you want to measure each current of the string and the voltage of 8, 16, 32 strings in parallel, depending on the module power. Then you have combiner boxes. Combiner boxes are then collecting the current which goes to the inverter. So we measure all the inverter parameters. We can and also the transformers and temperatures. And then you want to measure also the grid connection points, power quality, power meters, and also the official feeding meters. In big power plants, you have several meters. You have incoming energy, outgoing energy, and so there are power plants with 10, 15 meters, also quite common, especially when the ownership of the power plant has multiple parties. So then we are collecting all the data, and the people are looking on that data. Next to that, we are collecting, of course, all the environmental parameters, irradiation sensors with reference cells, parameters, wind, module temperature, ambient temperature, and so on. And this is more or less a setup. And you have a weather station for each 20 meg or 10 meg, depending on the customer's requirements. You have, if you have decentral inverters, you just read all the data from the decentral inverters. So we do all the protocols there. And this brings then thousands of channels per minute, in our example here, to the data logger. And then we have all the data normalized and pre-calculated. So we can do the enrichment quite easily by the customer. So we have all the reference values and so on. This is in the range of, for a 100 megawatt plant, you have roughly several hundred thousands of parameters each minute of time.
Yeah. And I mean, everything is run now by computers. One could naively assume that collecting data is a simple work to be done. What is the complexity in so much data? Could you describe us why is it so difficult, and why Gantner has so much success in various industries in collecting data?
It sounds obvious, but it depends always what you want to do with it. If you know that very well, it's an easy task. When we want to measure temperature, you buy a data logger, connect a temperature sensor, and you have a display. Yeah. But it depends on what you will do with that display information, because you want to store it over time. So you want to see what was my temperature over the last day. And when you want to see the last year, you need an uptime of 99 whatever %. So you maybe don't rely on a Windows PC or any Raspberry Pi, which has a firmware update, and after the firmware update, it is not running, and you have to do the configuration again. So these are typical things from what all consumers know. And when you want to do that for scale, and you are responsible that each minute the data is there, you need solid hardware and solid connectivity.
Yeah.
And you need UPS. If there is no electricity, you still want to log the data. You need different interfaces because each sensor behaves differently. We have all plugins there that you can speak to, all the Modbus versions and so on. And especially at the beginning of the solar boom, each inverter manufacturer had different protocol nuances, so you have to be flexible. It's not perfectly standardized, even when there is a standard. I think you all know that game. And then you also need the ability that others can have a bidirectional communication so that you can send a signal to the data logger, which is then sending the signal again back to the inverter and say you are doing power reduction, or you're doing active or reactive power and so on. So the control mode comes into that. And we combine everything in the same platform, which makes it cheaper for the customer because you don't have a monitoring and a control separately.
Yeah.
Doesn't make sense.
Okay, so reliable data logging is the key here, so that it doesn't break down, because your customers really depend on high quality data, and then also the usability with the bidirectional communication. What's exactly the value you create? Is it more on like initiating preventive maintenance, or is it more on optimizing your solar power plant or any other operations, or is it both? Where do you think is the largest value you create? Preventive maintenance versus optimization?
It's both or all of them. All again depending on the target customer, because first of all you have to have a track record of your asset. When you want to sell your car, it's good that the counting number of your distance is reliable. So you rely here that this is traceable and protected. So you need a good data quality, which shows how much energy was that asset producing, what are the failures. So it's having data of that asset gives you a higher price when you can sell it in the secondary market. The second thing is you want to optimize the data. So when you're a kilowatt hour driven company, you can find out where I'm losing energy. And this is also where we provide here the services, and you can visualize that, have all the alarms there, and you can also have the models comparing that. So we can tell you for any given point of time what should come out and what is coming out, and based on the difference, you can trigger your alerts. And when you have data over time, you then can do the preventive maintenance discussions, which I think is at the beginning of being implemented into the real world. There's a lot of buzz around that, but the question is who really runs that in the big fleets and not just for a prototype or for one or two power plants. And even for that, you need high quality data. You cannot correct it over time. And here, the big companies are having their own teams working with that data and accessing to our APIs because we have quite frequently the thing that we have the data normalization already perfectly done, so their data scientists can work faster instead of setting up a separate cloud environment. That's a key differentiator. So we are saving manpower.
Okay. Now, when we look at your customers, and maybe you have insights in simply by the questions they ask you on what you should change in your product or services. What's the key challenge in operating solar power plants? What keeps your customers busy night and day?
When you enter new areas like Middle East or Australia, which are remote, and you're a German EPC or you are a European EPC and you go abroad, it's logistics and to have the right people there and realistic and reliable communication of what do I need. And central point of information is key, so that everybody has the same information and the same SLDs and all that stuff. And that's number one. So it's the team which is established, and a lot of great EPCs and customers have these teams ready, and they can really do that on scale. That's really good. When you have that, you need somewhere the data so that you can support that from the office. And we don't have a big team flying around. We can do everything from the office with our remote access services, and people can prepare everything in the office and then go online. And if you have problems, we can log into all the devices and support them. That's very helpful for commissioning. And overall, later on, it's the adaptability that, yeah, you have phase one and then you want to add phase two, and this has data streams have to come together. So this is also very important that people have that ideas. And when you do that 3 steps, you have to have a flexibility, but still robust platform, which allows you all that things. And this is very key. And the demand, what people want to do in 3 to 5 years, nobody knows. It's not clear. You have to act very quick. And on top of that, it comes that different countries have different ways how you control power plants, how you have to monitor power plants. So you have to be very country specific. And it's not that there is a standard way for it, that you have a standard monitoring concept. You have a starting thing, and then you adapt it. Where a lot of more standardization comes in, when the big utilities build up their portfolios, they want to harmonize it everywhere. So they say Gantner monitoring has to be here. That's the component you have to use. You can select this types of modules. You can select this sub construction company and so on. So there it is. And when you have then power plants built in that pipeline, then you have a lot of repetition and a lot of good learning effect, because people know how it was in the last time.
Yeah,
that saves the most cost, I think, nowadays.
Okay, yeah. So it's cost, and one thing, and the other thing is reliability. So do you get insights on how reliable solar modules are these days? Inverters are always said that they break down mostly after 10 years. Or in general, what is the weakest component in a solar park nowadays?
Well, that's the holy grail. Everybody wants to have the insights, and I'm not able to share all what we see, but I try to share what I think is gives us enough insights.
Yeah.
The reliability of power plants also depends a little bit of the year or of the era they were built. I mean, if you know what was done in Spain with the big solar boom, now there's a solar boom again, and they learn a lot. They do it differently than in the past. Also, the big solar boom in the UK. Power plants are built up, and after 1 or 2 years, they are sold to another one, and they then observe what happens after 5-10 years. And it's really the important component is always the inverter, and the communication of the inverter is also something which is very important, that this has to be reliable.
The communication of the inverter with the data logger?
With the data logger, that's an important thing, because when the inverter is not able or stable enough to work 24/7 and send data, and you have to reset it, this is something, as an example, what are early failures. And we also work with a lot of inverter manufacturers together and optimize and give feedback, and then we have to update the firmware so we can roll that out to the whole power plant with one click. That's a thing. A second thing is that the components are not able to adapt to the electricity codes. I mean, power plant control is now required everywhere. So if the inverter does not have that ability, you have to exchange it, and then you're losing money, and it's not controlling fast enough. So this then creates a failure.
Sorry, can I jump in? What kind of communication is that? So the inverter receives messages from the grid for what purpose? And
For okay, I mean, power PV is a significant player now in the energy generation, and therefore you have also to support the stability of the grid. The 50 hertz has to be stable. So the big power plants, and now also smaller power plants, have to be controlled. So the utility or the DSO is sending signals. I want to reduce your power, for example, to 80%, and then this have to be executed. If this inverter is not able to do that reliable, they are shutting it down. Then you lose everything.
So the grid operator shuts down the solar park because they say you don't follow our rules. Yeah.
Exactly. So that's one idea. Another thing is really that you have to react very quickly, and then the ramp rates of inverters have to be controlled and so on. And here we try to bridge the problems from the limitations from the hardware to the grid, to really adapt to the real use case. But it's also about failure. The question, cabling and basic engineering, that you do it properly, that the cables are protected from the environment, also something that a lot of people had to learn, especially when you're going outside of Europe. You understand why in Australia the cables are sealed and protected, and sometimes with metal tubes and so on. Termites and all that stuff is really something which you have to take care about failures. And when you have all the basics done, then you start to see, okay, how is my PV device working? And that's also very interesting, that how you get different qualities out there, and how the different batches work. Of course, you will see that in the meter a little bit, but always half a year too late, maybe, that you have a problem in degradation. So our job is to really detect that and at least flag there is something running off. You had a lot of interesting insights when you have PERC technology at the beginning, and so on. And a lot of customers are really looking at that from the beginning, so they want to see the LID effect and so on. And we could really help them to give feedback also for the from monitoring to their lab-based measurements to their quality operations and so on.
Yeah. Okay. So you're looking at the big picture, Gantner, like at complete strings or the complete solar power park. There are how large is the need for, like, let's say, individual solar module measurements? There's mobile labs, so you can do quality control on site. There's inverters per module, which are mostly used in the residential area, but of course, in theory, could be used in large solar parks as well. So in general, what's the need to have in situ, or let's say a more complicated on-site individual solar module measurement?
That's a good question, and there's no one sentence answer to that. It depends again really on what is your target. I think the big players are all investigating the technologies up front, have their own test labs, have their own test facilities, do the indoor stuff. And for all the components they install, they have the quality inspections, but that cannot cover how the device behaves over time. And when you know how your technology degrades, if it's degrading, where it is degrading, you can adapt if you have the problem later on in the field with a rearrangement and so on. So if current is degrading, it's different than when you have voltage degrading. If you have to repair stuff like that, that helps. But that's everybody hopes not to have that problem. So they try to test and at least work a lot with statistics and say, I tested X% or fraction of a percent of modules and sample that, and from that I know how this is distributed. So here I think it really makes sense. When you have string monitoring, you can have a lot more insights on the module level versus just decentral inverters. So that's why string monitoring is sometimes added for research projects, also on small power plants. But when you have the IV scan, you really know what's going on. And I think this is very important that you understand there, because it's not just the maximum power point area which counts, it's also how is the parallel or series resistance changing over time. And this is where we give additional insights, and we did prove quite lately, and also with a lot of publications, that you can also understand from one module the whole string and conclude a lot of fault behavior from that. So string IV scans always make sense from the representative module.
Okay, so you can do IV scans with your product. I mean, can you give us an idea how you do it? Because you only have access to the full string, or do you have a device per module? How do you do it?
We have a separate product line which is doing IV scans as a solution that's not connected to the power plant, but we can then overlay the data and learn from that. So that's one thing. Another thing is that you can also ingest IV scan data to our platform from a third-party device, and then we can correlate it there and also try and also model it. But the question is always, how correct is that? Because you cannot work there with 1 minute average irradiation values. If the sun is moving, you need a higher resolution. So IV scans are done in a second. So you have to have the right data acquisition. So we rather add this feature set as a separate system to big power plants or for big customers to offer that service, and then you overlay the data. Because when you keep the PV module at MPP between all the IV scans, the results show very clearly that this is very realistic how it is going on, and you can also it's much more simpler to work with the data. So that's the way for the IV scan. Also for companies which are doing PV module development, research, or quality, IV scans are always helpful to link that from indoor to outdoor.
Okay. So that's an extra device you connect to a string, so then you can do different IV scans at different temperatures, different irradiations level, and do that over time. So you have lots of data, so you can track degradation or any funny effects very early. Okay.
Yep.
Okay. Then there is the non-contacting or partially contacting technologies like imaging technologies, electroluminescence and infrared imaging, sometimes done more and more done with drones. What do you think of that? And maybe can you even integrate this data automatically into your system?
Yes, I think that topic has big potential and will grow further and further, because it's a different way of getting insights. And I think it's not one or the other. It's when you can combine it, I think you can save money and time. So if you have current of a string and you have a picture of that string and you see how it is behaving with the module temperature or EL and so on, then you can draw fast conclusions. And how we can work on that topic is that people can access our data with APIs structured already, so you can overlay your picture information with the measurement overlay information and work out here some conclusions. So that's possible as of today. And somebody has to work on that enrichment step. And I think this is quite in the build up. So we provide here the API at the moment. I think at the end, you cannot avoid that somebody has to go there. So it's a quick thing, and if you have no monitoring, it helps you a lot, and also see that over time. But also that service is not for free, and it's just at the given point of time. How much, when you want to run that drone every week, okay, that the question is, what is the price for that? I have not seen here a business which is profitable. So they rather do it yearly and so on. And then you have to also be clear about the precondition. Is it cleaned? What is the angle of incidence and all that stuff? So it's very interesting. And I think the challenge is to overlap that with a real measurement. And then you have the right insight, what you think you get.
Yeah. What do you think? What are other innovations required to optimize solar park operation and maintenance? So we just talked about drones. You have introduced a IV scan methodology. What else would you like to see in the future?
What I think is key, that the data you have, that you utilize that. A lot of people are collecting data, but they are not utilizing that enough. Because the first one is the number of data points you have, and that's not something what you can do on your PC. You need really a platform which can handle that, and this is where we work a lot, that you have structured scalable data backends, so that the people can get their data quickly when they need it, and out of that data you can do much more analysis. So I think it's underutilized. And the second thing is what I would do before jumping into any machine learning era is, let's call it the era of metadata. I think the efficient combination of data, measurement data, time series data with the meta information, that has to be solved, because I try to explain that. So
yeah, well, what's metadata?
If you have a time series of the inverter performance from yesterday, that's time series data. You can plot that, but you have to normalize it. So you need the nominal power of the inverter. You need the brand, you need the serial number and all that stuff. And when you can access that quickly with one API call, then you can start to analyze very efficiently. And a lot of people spend a lot of their lifetime to combine that data, build it up, and when
manually,
you say, exactly, can I have it for another version? Yes, go back to square one and then do it again. Okay. And this is where our next improvements will be. We have already all the metadata from the components inside, and that makes it easy for the people to quickly do their conclusion and do basic analysis to solve the most important things on a daily work. So I think that's quite important. And if you do it right at the beginning, you save time. That's something what I also see a lot. Don't wait, do the setup correctly, because you need it over decades, and every person who will use the data can use it. And if you have the wrong metadata connected, all your work is not helpful. It's not true. So metadata, I think, is key to combine that.
Okay, so if I summarize correctly, correct me if I'm wrong. So number one is use the existing data more wisely, work with it. And the second is add the metadata like serial number, product generation, etc. So add more information, and then again, I guess back to topic one, work with it and work with it more wisely. So you don't need, let's say, hardware innovations. It's more like work with the data, create more data and work with it.
And use what is available. I mean,
use it.
When we collect really everything what the inverter tells us, even when it's not required, because we know later on the customer will ask for it. So it's really collect the data. You don't have to store it forever, but with the experience, we know that a lot of that, for example, inverter temperature is important. At the beginning, nobody wants to have it, but no, when you start to do aging and things, you want to see the temperature profile of all that devices, and quickly you can find out, oh yeah, if you forget the shade cover of that inverter in Australia. That's worth it, you know. Stuff, simple example.
Yeah. Let's jump to storage. Obviously, as we have more and more renewable energy in the grid, we need storage to compensate for phases where there's less sun or no wind, or even worse in combination. So you mentioned that you also have solutions for the storage battery sections. Just briefly, what is the key challenge here? What's the industry now keeping busy most of the time?
That's a very good question, and I think storage will or has the potential to be a similar, even why not a bigger success story than solar. So that's what I think, and you see also that the market behavior at the moment has a lot of similarities to the PV gold rush when we started 15 years ago, something like that. This is what I see. I think batteries have one more or two more additional complexities. First of all, the business model will change over lifetime. And the second one is, what do I get? So here monitoring and quality control is even more important, because you have to keep your device at the right temperature, at the right environmental conditions, to not lose any warranty claims and all that stuff. So from the delivery, that's important that this is monitored. So this is where we support. Then you install it and you try to run your service. That could, you know, there are more than 23 different services are out there for batteries, different on the things. You can have energy arbitrage, spinning reserve, frequency regulation, and black start and all that stuff. But you could also do just peak shaving or backup power, or they had the triads in the UK where a lot of business was done. And if you take the peak shaving example, so we want to shift the peak from PV to the evening, which is more or less now the #1 use case in California or in the southeast of the US. Then you do that and you try to collect the energy from the southwest in Arizona and Nevada and provide it to California when there's sunrise and sunset. And when you have changing energy prices, electricity prices, people could say, well, I earn more money when I do frequency control. So let's do frequency control with my asset. And then suddenly you have to be able to control the batteries differently to switch the mode. And this is something what is new for all that players. And this is where we really adapt on that. You could run different control methods at the same time and for the different assets, because the investors see different opportunities. And I think it's not clear what the batteries will do as a service in the next years. The market is changing very fast, so you have to adapt. And when you make that decision, you also need some history, how many cycles I have done, how is the aging of my battery. So there is also a lot of battery analytics done. And here we are, the industry as its own is learning, is developing skills, and a very fast driver is the mobility section, where they really try to understand everything.
Yeah, excellent. Hey, let's come to an end. One final big question, and when you look at the outside Gantner, outside monitoring, you've got many years of experience in the solar. You've seen a big rise and regional drops in the application of solar, and now there's a big turn up again. You see the day-to-day operation of solar parks. What is required from your point of view, to take solar to the next level, including storage, including wind? So so that it becomes so that it's used more often, more quickly, more globally. What is required to make that possible?
Big question. Try to answer it in a not if it's a big answer or long answer, but I think we all see that the energy system should be decoupled from the gas price. This is what helps us, because then it comes out what is the energy production cost of solar wind, and it's the cheapest. So it has a lot of momentum at the moment, and it will keep. I mean, we will see more than 50% of the energy capacity installed will be solar. That this is growing. We have this is momentum cannot be changed. I think that's very good. The question is now how you put that into the market. It has to work reliable. You have to have it like a good concept where you can adapt it at different places worldwide, and it's scalable quite fast. But you have to keep the quality. I think this is important, and it has to play a significant role in the grid stability. So you meet in the middle. You have the big utilities doing the stable grid, and you have the smaller players from renewable energy. So you have to be part of the grid of the future, which will be smart in terms of that it is not centralized anymore. I think this is needed, that you remove that barriers, and these barriers should be removed. And I think there is a lot of speed reduction tried by a lot of players, because you lose power when you have an established energy system with the big players, and when it's decentralized, you cannot. The market mechanisms work differently. Mm-hmm. I think this is the big thing. The technology is there. You can always improve it. You can reduce CO2 footprint and all that stuff. All this stuff, I think, is going on. And I think the data on top of that should be available and used for all of the participants in the power plant and in the energy segment, that you can really optimize that smart system. Mm-hmm. And data quality, I think you cannot argue about that. If you have good quality, you can have good control.
Excellent. So a decentralized energy system with a smart control, that's the key point you see as to accelerate the rollout of solar and energy wind production. Yeah. Excellent. Hey Jürgen, thanks a lot for your insights. Thanks for taking the time, and all the best for you and Gantner.
Okay, thank you. Thank you for the opportunity to share our story, and I'm looking forward to meet soon in person again.
Yep. Bye-bye, Jürgen.
Bye-bye.